Okay, so I cloned the repo for today, and our lecture task is in here. And as I said before, it's basically two parts. We have one part that is correlation and regression. We don't really do this very detailed. It's just we scratch a bit the surface and like kind of show you that it's possible how to calculate a couple of important correlation metrics. And then we start doing stuff with spatial data. And especially with coordinate systems here. Yeah, but we start off with some more statistics, respectively correlation and regression. I hope you've heard about that before, or like learned about that before. I'm relatively sure you have. Yeah, correlation and regression are two important methods in statistics to analyze relationships between variables. And correlation is basically how strong are two variables connected, or are they connected at all? Then is the relationship positive or negative, and is the correlation significant? But important, that's general advice when it comes to correlation. Correlation doesn't have to be evidence for causation. So stuff can be mathematically correlated, and that doesn't mean the one variable causes the other variable to behave like this. Stuff can be, especially if you have data that is similar in similar distributions, stuff can be correlated without any reason, just by chance. So be really careful with what conclusions you try to draw from correlation. And then we have regression, which is usually used in pair with correlation. And it describes the form of relationship. Is it a linear relationship? Is it a nonlinear relationship? Linear relationships are really easy to explain and really easy to do regression for. Linear regression is maybe the most simple and basic form of regression we have. Nonlinear relationships are harder to describe and to capture. Regression is all about how does one variable change as a result of changes within Y, and it is frequently used in analyzing trends. So what we do today is we go back to yesterday's climate data. If you remember, you had these climate 2021, and we have it's kind of a multi-purpose data set. We have this climate data from yesterday, and we have a second data set. I showed this to you in GitHub before. That was called Ratszähler.csv, which is a statistics. It is a statistic on cyclists who crossed the Adenauer Bridge in Bonn. So if you know that bridge, it's a bridge over the Rhine, and in front of the bridge, and on both sides, I think there's a cyclist counter that counts how many cyclists go over the bridge, and I think it even shows on like a sign. And these are this is basically the data set from a part of 2021 out of this cyclist counter, and we will use that to find out if there is a correlation or a relationship between good weather and cyclists on the bridge. All right. So these two data sets are already in the same local repo now, and if I'm not mistaken, R should already decide that this repo is my working repo, which is correct. It's day 4 statistics and plotting 2, and then my name. So that's really comfortable because it means we can just get rid of all this here and only can use the relative file path to load this to R. So we just load this climate 2021 data set, which you already know from yesterday. No such file or directory. That is unfortunate. Let me check. Wow. Okay, I apparently I forgot to put that into the how do you call it, into the repo for today. So we still have it because it's the same that we used yesterday, but this complicates things a little bit because now I have to dig up the file path. I'm sorry, this should have been in the repo for today too, to make things easier. But you still have this data set from yesterday. So what you have to do now is, I don't think you can see it because my screen share is only in our studio. But what I'm doing now is I go into the local repo from yesterday, which is, and here is our data set. And now I take this data set and copy it into our folder for today. And then I save this. And now it should be here and hopefully will be detected. Yes. All right. So what you have to do here is you go into your folder from yesterday and take over this Klimatag 2021 02667.txt, which is the climate data from yesterday. I apologize, I'm sorry, I forgot to put it in here. And you just copy it into the folder for today. And then you can still use the relative file path. Alternatively, you can use an absolute file path to the folder of yesterday. That's fine, that will work too, but it's a bit longer and more annoying in my opinion. And then our second data set here is the Ratzeller.csv, which this time should be in the folder. So I just remove this and run it. And then you can see here our cyclists. Let's take a look because we don't know this one. So we have basically a couple of days in a column. It's dates. And then we have Kennedy Brücke. I think I called it Adenauer Brücke before. I'm stupid, sorry. Kennedy Brücke north side and Kennedy Brücke south side. So this side is the northern side and this one is the southern side. And it counts. And you can see, which is a bit weird, that sometimes there are more people going into the north side than they're coming out of the south side, or the other way around. So there's a difference between north side and south side, and I'm not really sure what that is. I think the counter might not work correctly, or sometimes cyclists get obstructed by cars or like people who walk by foot. So there's a lot of, or some discrepancy in this data set, unless 200 people spontaneously decided to jump off the bridge instead of cycling through the end. Okay, but this is our data set. It's a very simple one. It's not very big. It's just 19 observations, so 90 rows. And then what we do here is we rename a couple of columns in this data set. Maybe it's more clear if I show it before and after. So before we see these names aren't really pretty. They have like weird symbols here where the German umlaut would be, and they are really long, and we can easily rename them. That's something we did yesterday too, I think, if I'm not mistaken, using the names function. And the names function is a rather simple functions where you can get or set the names of an object. So if I just call names cyclists 2021, I will just get all the names of the columns in this data set. But if I want to override them, I can use this function and then combine the new names into it. So let's do it like this maybe, and then have it capitalized and in English, which is of course personal preference here, like this. So we rename our 3 columns to day Kennedy North and Kennedy South. And if you look here into the data set, you will see the new names, Kennedy North, Kennedy South, and day. Then the first thing, if you have a data set, as usually you try to plot it, or you try to plot parts of it just to get an understanding of what's going on there. And if we try to plot, whoops, I was one step ahead. We go back one step. I completely omitted this line. What we want now is we want a new column, because Kennedy North and South are nice and fine, but we want the whole, like the 2 columns added. So we create a new column and we add the Kennedy South column to the Kennedy North column to have a Kennedy whole column. Now this is in German and that's not great. Kennedy guess stands for Gesamt, which would be Kennedy whole. Let's just call it Kennedy whole, but with a big K because we used the big K before. So this you already, I'm not sure if we had it in the lecture script yesterday or if I just talked to you about it individually when we had the breakout sessions. But you can easily, I think it was in the lecture script, you can easily calculate a new column just by referencing it with the $sign. Like this column, Kennedy whole, it doesn't exist yet, but it will exist because we are assigning something to it using the sign arrow, if that's clear. And what we are assigning into it is we assign our column cyclists 2021 Kennedy North plus, which is possible because it's a numeric. You can see here it's numbers, so you can just add them, plus the Kennedy South. So the issue we have now is we have changed the names to English names. I put this like this so it's easier to read. We have changed the name to English names, so we have to change them here accordingly. So this column is no longer Kennedy North, it's now Kennedy North. And the same thing we do here with Kennedy South. And then we run this and look at our data set, and then we see here a new column that's called Kennedy whole, which is just Kennedy South plus Kennedy North. All right. And now we can plot this column. I'm sorry, I forgot to change a lot of German designations here, but we can easily change this. We can easily plot this column Kennedy whole to see how many cyclists went over the bridge. And this is just without any style settings or parameters. You can see a simple like scatter plot, and the index is the dates with 19 observations. So the x-axis is 19 entries long. And then we have here the number of values. So the number of cyclists going over the bridge. All right, so that already looks like something is going on there. We can't really tell yet what, because it's just a scatter plot, but we can fix. Can fix it by giving more arguments here. So you could change the type to line, and then you have a line plot. And then it looks like this. But for now, I leave it like this. You can apply all these style settings you learned yesterday to this plot. It's fine, but we just leave it like this now. And now what would be interesting is to see in this plot maybe how many precipitation we had. Because if you remember, in the Climate 2021 dataset, we have this column called Niederschlag, which is precipitation in millimeters. And we assume if the precipitation is really high, that there are less cyclists going over the bridge because nobody wants to cycle when the weather is really bad. So this is just one suspicion, like it's something that could possibly be. And to kind of confirm or to kind of check if we are onto something here, we can add a line using the lines command, and this is just the same we did yesterday for the precipitation in millimeters. I just run this, and then you will see what happens. And then we have the precipitation in millimeters here. And one thing we do here is we index it, so we only take the first 90 values. That is because our cyclist data set is only 90 values long, has only 90 observations, so 90 days. And our climate data set has 111, so it's a bit longer. And the reason we can do this so easily here is it might not be so easily with other data, is because they are ordered in the same way. So these are ordered by day. So you have day 1, day 2, day 3, day 4, day 5, starting from 1st of January 2021. And here in the cyclist data set, you have the same, starting from 1st of January 2021, and then going down the dates. And this multiplier here, we can see what happens if we remove it. I have to plot this whole thing again, I think. Like this. Yeah, you see what happens if we remove it, and that is nothing at all. And the reason for that is that our precipitation is in a very different scale than the cyclists, right? Our precipitation, if you look in the climate data again, is like 0 or 70.6 or 10 we have here, or extraordinarily high 31.8. But the cyclists are in a much like larger scale, in thousands. So we are not able to see this here because the scale of the y-axis is far too large. So to address that, we just multiply the values of precipitation just to see it actually in our graph in a meaningful way, or like have it represented in a meaningful way. And what we can see here is indeed in the days where we have no precipitation at all, we have a lot more cyclists going over the bridge. Not in all locations, but this is the 1st of January, generally very bad weather, and also people have holidays. So we're not sure if there's a correlation yet, but we can kind of see that something's going on here. This is a bit, yeah, it's a bit arbitrary. You could also use 300, yes, and it would look like this. Yeah, obviously now it's plotted over the thing, so maybe like this. Then the values are a bit smaller, the scale is a bit smaller. Yeah, it doesn't matter, it influences how the plot looks, but this is not our final result, right? So we just did this to like find out if there's something going on in this plot here. But if you multiply them by too much, then the values will become so large that this line will no longer be any meaningful anymore. Like this is maybe harder to read. Or if we do it like 10,000, it will be terrible. Will look like this. Or if we multiply it by 10, then it's barely noticeable. Like then you can still don't see any line here. So we try to find a value that's meaningful for the scale we have on the y-axis here. And for now, just go with 300. Okay. Again, here we have the issue that I have the German column names. Then we do something that we didn't do before. We plot the density of something by using a nested function. So this is a function inside of a function. The outside function is just plot. So it tries to plot something, and the inside function is density, which we can look at like this. The density function calculates density estimates, and then a bunch of other stuff that's not really important for us now. So to plot the density, of course, we can use this density function. And we can also do it for the presentation. We didn't change this, so it should be fine. And it looks like this. Yes. So the density function, the density is a little bit, it's a bit similar to a histogram, but in a different form. So it shows you how many kind of values are in a certain value range. So in the density of the precipitation, we see here that the precipitation is dense between around a bit above 0 millimeters, like 0, 2, 1, 2, 3 maybe millimeters, and then we have smaller peaks here at around 4, 4.8, something like this. But mostly you see there's not a lot of precipitation, or like not extraordinary amounts of precipitation going on in our data set. And then we can do the same for the cyclists, and we will see yeah, the most dense, or like the frequent amount of cyclists was around 400, 4,000 and 5,000. And the reason why this is different than the histogram is, I think it's more readable, in my opinion, than a histogram, and it doesn't use the steps like the breaks that a histogram uses, because it's a bar plot. So this is very good to get you an overview over how your data is concentrated. So now we go into our first correlation test, or maybe we don't, because yes, we do. We still have some time. And I'm not sure how much statistics I should have to explain here, because theoretically you should know what the Shapiro test does. But I will try to explain some, but not everything and super detailed. Though Shapiro test is a kind of hypothesis test that tests for normal distribution. So using a Shapiro test, you can estimate whether your the data you have is normally distributed. So it looks like a bell curve like this. And the function to do this Shapiro test in R is called Shapiro test. We can use the help function just to get some more info, but it's super easy. So Shapiro, the function Shapiro test performs the Shapiro-Wilk normality test. You give in any kind of data set, and then it will give you out the Shapiro value, I think. And in our case, we want to perform the Shapiro test on our whole Kennedy hole column and inside of the cyclist data set. Okay, while you look it up, I just do the same for the first 90 entries in the precipitation column of the climate data set, just so we have both.
basically, the smaller the p-value, as far as I can see now, the bigger is the chance, the likelihood that it is normally distributed. And that's also what I had in mind.
It makes sense, right? Because this is very clearly almost normally distributed.
Yes. So
it has a tiny p-value. It's even tinier than for the cyclist.
Yes, I think. Well, I need to look it up certainly, but zero would be like perfectly normally distributed. I think there's this threshold of 0.05, but I'm not entirely sure. Yeah.
Okay. Yeah, but small is good, and we can see the difference between him. This value here is it looks larger, but it's smaller because of scientific notation. And you could also visually see the differences in distribution in this data set. So this data set is less less close to a normal distribution than the other one. And so it's much closer to the threshold. And what you do, or what you can do after the Pearson's, after the Shapiro-Wilk normal distribution test for normal distribution, is one of many correlation tests. So you can test for correlation. It's the same method with the hypothesis tests. I'm sure you had this, you were tormented with this in school and also in your studies already. And I think the most most well-known correlation metrics for the test for linear correlation is the Pearson's correlation coefficient. And Pearson, not a great guy. I think he was horribly racist and in general, not a very likable fellow, but his test is okay. So we still use it in science today. And the way you do this correlation tests, all of them, in fact, is the function core test. And here you can test for association between paired samples using one of Pearson's product moment correlation coefficient, Kendall's tau, or Spearman's rho. So you might remember these from statistics. Kendall's tau and Spearman's rho, different correlation coefficients. We use Pearson, and we define this with this argument here, method equals Pearson. But if you use method equals, I don't know, Kendall, I'm not very sure, not sure what the correct argument here is. Yes, Kendall or Spearman. And then you can use the other correlation tests too, if you like that. All of these tests have different assumptions and are slightly different and have different applications. So you have to look into that before you just start testing away. But now we're at the Pearson's correlation test, which is super easy to pull off. You just have to give it two variable sets. In our case, we want to test the Kennedy hole and the precipitation, but only the first 90 entries, because you remember this data set is only the cyclist data set is only 90 entries long, so we have to like limit the other data sets so it's the same extent. So we want to test correlation between those two columns, or like the values in those columns, to be precise, the Kennedy hole column and the precipitation in millimeter column. And the way you do this is you press the button and things happen. All right, and now we calculated the Pearson's product moment correlation. And the p-value is relevant for the significance again. So this, I think this is the correlation coefficient, the minus 0.299, and this is the confidence interval of the correlation coefficient. So it goes from minus 0.47 to minus 0.09, and our coefficient is minus 0.299. And if you remember from statistics, the Pearson's correlation, product moment correlation has a value range from -1 to 1. And the high values or the low values respectively are a high correlation. So 1 would be a perfect correlation and -1 would be also a perfect correlation, but the negative one. So it also shows you the direction of correlation. And in this case, we have a small but statistically significant because of the p-value is lower than, I'm just assuming it tested for 0.05. So we have a statistically significant negative correlation, slight negative correlation here. So again, if you try to, or if you want to interpret this, you can very easily find this in any statistical textbook or anything in the internet. Just so you know how to do it. All right, so we did that, but now let's create a scatter plot of the two values against each other. Or I keep talking of values, but it's the columns, the values in the columns, of course, I'm referring to. So let's move this one a little bit to here. You will see why very soon. And then we created a scatter plot of our Kennedy whole column and the precipitation in millimeters. Of course, again, only the first 90 values. All my, I think I accidentally wiped my environment here, so I have to go back and load this to R, rename the columns, add the new column, and I think that's all. Yes. All right. So we create a scatter plot of those two variables. Here on the y-axis, we have the amounts of cyclists, the amount of cyclists going over the Kennedy Bridge in Bonn. And then on the x-axis, we have the precipitation in millimeters on the day. And then you can see all the high precipitation days have a lower amount of cyclists going over the bridge. But still, we don't see if, no regression line or something. We don't have a model to like model this visually. So we create one, and this is this section here. We create a new variable called lmfit, and the lm function is a bit extensive, and I wouldn't say it's complicated, but it's a bit more extensive. But what lm does is it fits a linear model. So it basically creates a linear regression between two variables. And there's a lot of arguments in this function, and there's a lot of stuff to know about it. But right now we use it only running on default settings to create a linear regression between our kind of the whole column and the precipitation in millimeters. And you will see what this does very soon when I run this. It creates a list of 12 called lmfit. And inside of this list, there's a lot of different elements, coefficients, residuals, effects, rank, fitted values, assigns, and so on. And that's all very technical and you can use this for various statistical analysis. It suggests here you can use it for single stratum analysis of variance, covariance analysis and stuff like that. But we're not doing any of that, and we're not carrying out regression right now. We only want a cool line in our plot. So that's what we do here. We add to our scatter plot here an app line. Remember yesterday, we use app line to create a horizontal or vertical line. And we base this line on our linear regression model, which is called lmfit. Give it the color red. And then if we run this line, we get our linear regression through our data set. And here you can see what Pearson's correlation test already told us, that we have a slight negative linear correlation between the two variables. So negative because the, how do you call it? The elevation of this graph is negative. A positive correlation would look like this. But it's not super prominent. Like it's not the strongest linear correlation that exists, but it's still significant. So we have some kind of relationship between how many people go over the Kennedy Bridge on a bike, cyclists go over the Kennedy Bridge, and how much precipitation in millimeters we have. And this is also what we would expect. Logically, people don't like to cycle when it rains, except if they have to, or if they are really hardcore cyclists. Yeah, but this is already quite good. This is quite usable. And you can create this linear regression and add it to your plot using the LM function, and then adding an appline of your linear regression model. And then what would also be interesting, maybe, perhaps, is to see how many people came out of the north and the south trackers. Because if you remember, in our cyclist data set, we have not just Kennedy Hall, which we calculated, but also Kennedy North and Kennedy South, which is how many people passed by the north tracker and the south tracker. So we can easily do this. And here again, sorry, I did change these variables to the new English names. Why doesn't it show? It's really inconvenient. Because it's wrong. I added the wrong number. So we take the Kennedy South column out of this table, and we plot a line graph and use color green. I don't like the color green. Let's do it with blue. It's really hard to read on the white background. Like this. And then we add to our line graph a second line based on Kennedy North, this time with the color red, because we already have blue. So this will be added on top. And you can see here what I talked about before. There is a slight difference between the numbers are functionally similar, but there is a difference between the numbers that the cyclist that passed one tracker and the cyclist that passed the other tracker. So there's a numeric difference between the two. And I'm not entirely sure why that is. I gave a couple of explanations before. Maybe the trackers didn't work correctly or were obstructed by, the scan line was obstructed by people who walked by or by cars. I think here this is just the density to illustrate the same. So this calculates the density function for both of them, or plots the density function, I'm sorry. Yeah. That's not great. I don't like the screen. Like this, and you can see the distribution is somehow similar. As you have the same hill here, but there's a large numeric difference in terms of how the data is distributed between the two scanners, which is weird, and I don't really know why that is, but it's just so you know. So we did gloss over it. Yeah, but that's it for correlation and regression. Obviously, we didn't perform a real regression, so we didn't go ahead and try to estimate how the cyclists will behave, like how the number of cyclists may rise or fall with increasing or decreasing precipitation. We didn't do that. And also probably we can't do it because the relationship is not very strong. So we have a small negative correlation between those two values, but a correlation that's not that strong is it's really hard to analyze trends, or it's really hard to predict how the future will look or how one variable will behave when another variable changes. So it's bound to be very insecure. So that's why we didn't do it with this data set here. And also because of time limits and time constrictions. It's not super bad if you didn't understand some of the stuff we did, like the correlation coefficients. You can look this up easily. It's in every statistic textbook. You probably should look it up, just like we should look up how the Shapiro test function work, because it's super important to create publications and all that, to know, like, to perform data analysis. If you do quantitative data analysis, you should know this. But I think it's good that you kind of learn that these are things you can do and are. But we decided against spending more time on statistics, and instead we move on to spatial data, because this is a course for geographers mainly, or people who work with geospatial data. So we kind of try to keep the statistics part short and extend the spatial data part. And this is also what we'll do now. We will start with spatial data in R. Because if you remember, we have our infamous Bonn shapefile here, which is a spatial data set, and we have a couple of GPS coordinates too. So we'll work with that now. But to start off, maybe a bit of a test. What types of spatial data do you know? So when it comes to, in terms of processing, spatial data, we have a large distinction between two different kinds of spatial data, and that's what Anna very correctly said. We have vector data and raster data, and both of them behave very differently when you try to process them. And I would, based on my experience, I would say R is probably more apt at handling raster data than it is handling vector data. Of course, you can do a lot of stuff that you can do in a GIS and R. But sometimes it's maybe more convenient to do it in a GIS, like QGIS or ArcGIS, whatever you prefer, when it comes to vector data. And that's just my personal opinion. But yeah, maybe Julian and can have other opinions on that. I'm not sure.
No, I agree. I guess the main thing or reason why using R is if you have big data sets, especially big raster data sets, then it's extremely convenient to use R. But this is slightly more advanced, and I guess we won't cover this in this course, but I agree. For vector data, I would prefer using ArcGIS, and for raster, it's nice to use R.
Yeah. Yeah, it's a bit of a trade-off because you can do a lot of amazing stuff with R, but it might take you a long time to get into it if you're not familiar with the programming language that much, if you're a beginner. And then you have to kind of think if it's more intelligent to do stuff in GIS and like in a very convenient and quick way, because you will be quicker, even though it's objectively a longer and more complicated workflow in GIS, for example. So it's kind of, you have to think about when you try to analyze data. And then we have another question, which is, where can you get spatial data from? And I realize it's a very general question. Then we have a big wall of text here that we can maybe briefly sum up together. Usually spatial data is larger than numeric data. So these little tables here, they are barely existent as far as the computer is concerned. So this is like a matter of kilobytes. And if we have spatial data, we usually talk in megabytes and not kilobytes, or even in gigabytes, depending on what you have. I don't know if one of you ever worked with laser data, like laser scanning, but laser scans are very, very large point clouds, several gigabytes large. So we usually, when we have spatial data, and that's important to keep in mind when you work with any software, it's much bigger, and large data sets cause long processing times. Of course, that depends a bit on your hardware. So if you run your code on a potato, on a toaster, then it will maybe explode, make some creepy noises and take forever. If you have a really high-end PC computer and you do like multi-thread processing and like run it on several cores at once, then you will maybe have smaller processing times. Then we have this little info here. I already gave this to you, and I think in the very first lesson, but now it becomes relevant again. So all the code we used before, it wasn't very complex and it was super fast. It executed super fast. But if you work with spatial data, you will have longer waiting times depending on your system. And then you will kind of develop anxiety because the code keeps running and running and you don't know, does it really run? Did the program stop responding? Is the code being executed, or is it just like broken? And you will see this small little stop sign here that says, that's an indicator that your code is still running and that your everything is all right. So often you have to be a bit patient and overcome your anxiety. If you click the stop sign, RStudio will attempt to terminate your code. Sometimes it terminates the entire window. Sometimes it just crashes R if you press it. So yeah, you can press the stop sign but expect no success or like little success. Sometimes it just crashes your entire program. So make sure before you run code that you know if it's very large and like processing heavy, intensive, that you save your stuff and push it maybe to GitHub. Yeah, and this one is a no-brainer. It depends greatly on your coding approach. So some functions are more computationally intensive than others. So there's different ways of doing the same thing, and some are more efficient. But also your data, the larger it is, and also the processing power of your device will change how long your code takes to execute. So, and this can vary a lot. Like code can execute from anything from instantaneous, which is what we are used to in this course, to several hours or even days. So that's just something to keep in mind when we work with spatial data, that it's a bit different when the data sets are large, just to prepare you. I don't think we will have much issues in this course specifically because we use very manageable data sets. And then another thing that's important is we have a lot of different file formats. You know this already because you worked with spatial data before. There's like GeoJSONs, shapefiles, XMLs. When it comes to raster data, you have TIFFs, for example. So there's a lot of different file formats, and sometimes you might have to change the file format to work with it in R because it's not supported by R, or sometimes you will have to install or activate a certain package or library to deal with a file format. One example I know right off the bat is XML. XML files are not supported by base R, but there's a package and it's called XML. And if you install that, you will have access to functions that allow you to work with XML files. So now we start with a very simple thing. We take a look, here's a little typo. We take a look at on how to deal with XY coordinates. So for example, you went into the field and you took GPS measurements with a GPS device, and you have a table with XY coordinates, and you want to have that as a spatial data set. And that you can definitely do, you can do this in QGIS or ArcGIS, but you can also do it in R. If we work with raster data, we need a couple of packages that are quintessential, and you will need them all over again. And it's probably for geographer SP, RGDAL, which is the connection with the RGDAL library, and raster are probably something that you will become really familiar with, because these are the packages you need to have when you work with spatial data, because a lot of these spatial data stuff is not part of the base functionality. RGDAL maybe sounds a bit familiar if you use QGIS, because QGIS, a lot of functions are directly derived from the RGDAL library too. So we start off by installing the package raster, which I have already installed, but I will install it again just for now. Maybe there is an update. And here you can see now, because this takes a bit longer, this little stop sign to interrupt your code execution. So stuff happens, the raster will be installed. You can see SP is a dependency of raster and will be automatically installed if you install raster. I think the same goes for RGDAL. I'm not entirely sure right now. Okay, but then we call library raster to have it activated. By the way, one other way I think to activate your library, activate a library or a package is the function require. So you could also use, instead of library raster, you could also use require raster. And I think the difference between library and require is that require also activates all the dependencies of the package you're using. So maybe it's a better way to do it. It's like this. But for now, I will keep both options here. Functionally, they are not that different. So just so you know. All right, and now we have the raster package installed and activated, and we can read our shapefile, which I have put here into our repo, into R, using a function called read_ogr. It's very similar to the read CSV. So let's check if our relative file path is still working. It is. And since it is, we can get rid of all this and just do it like this. Like this even, sorry. Before you use read_ogr, I think, yes, read_ogr is part of the RGDAL package. So you have to call RGDAL, you have to install it if you didn't install it yet. And then you have to activate it. And now the documentation works just fine. So I assume that the function will work just fine too. And read_ogr reads OGR vector maps into spatial objects. So we can use it to load in vector data. So shapefiles, GeoJSON, everything that's vector data, you can use load into R using read_ogr. And if we load it, you will see it takes a short while, and then we get a new data set that's called Bonn. And it is a formal class spatial polygons data frame. Let's take a look at how this looks. So this is a lot of stuff going on here. So this variable is a spatial polygons data frame, which is basically a data frame, but we have a spatial reference. And here you can see the extent, which is the maximum extent. Here you can see the coordinate system, the CRS, which is WGS 48. And then long lab coordinates. You can see features, which is how many polygons are inside of this data frame. So it's 1 because it's just Bonn. And then we have a couple of other stuff. This is basically the attribute table here. Okay, nice. But what happens if we plot this? There we go. I don't know why we put this axis labeling here. Let's just do it like this. So if we plot this, we will get a visual representation of our shapefile, and this is exactly how Bonn looks. If you didn't know that, this is how it looks. A beautiful, very beautiful shape. So let's add the axis, and if you look at the axis values, you will see these are lat long coordinates. Okay, we have our shapefile, we have the lat long coordinate on the x and y axis. So this is basically a map. It's a kind of, it's not a very nondescript and very not very useful map, but it is a map. So now we have a bunch of coordinates. We have this GPS coordinates, coordinate mass coordinates should be clear, even though I didn't change the name. So let's just open this in Excel. And Excel hates CSV files for some reason because it's a Microsoft product, and I don't know. It has a lot of problems with the delimiters and showing it correctly. So these are not in different columns here now, but I would have to change the delimiter here, I think, manually in the options, but we don't, it's not important. But what you can see here is you have a bunch of coordinates, X coordinates, Y coordinates, and then an ID, which is just 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 coordinates. And here we don't need this because our relative file path should be fine. Here we just use the read CSV command again, just to read in our table. And then if we try to plot these, you can see we have here a bunch of coordinates defined by an X and the Y axis. And even though we now have our coordinates in R, they don't have a spatial reference. So there's no coordinate system. And R doesn't know which coordinate system it's in. Unlike a GIS, for example, it doesn't try to find spatial projection on everything you give it. So we don't really have a coordinate system for this data set, and thus no spatial reference. And that's why they also don't show up on top of our little shapefile. And the way you do this is really easy. There's a function called CRS, which stands for Coordinate Reference System. And that's also just very spatial data 101, right? If you want to use multiple data sets and want to work with them based on geolocation, the data sets need to have the same coordinate system. So they lie actually on top of each other. So what we want now is we want to know what the CRS function does. And the CRS function is used to get or set a coordinate reference system or a projection of a raster object, but it obviously works for shapes and vector data too. So no worries here. And we want our data set to have the same coordinate system as the Bonn shapefile. So we first find out what coordinate system the shapefile has. And this is the coordinate system for our Bonn shapefile. We saw this before here when I just called, I can do it down here. when I just called the name of Bonn, and it showed us a short summary of what's in that layer, or in that variable, there's an argument, not an argument, but there's a column called coordinate reference system in which we have the exact same information, and this is the one that calls if we call CRS Bonn. And now we want to write the CRS of Bonn into a variable. There we go. Now we have a formal class CRS. So it recognizes it's a CRS, and now the CRS is inside of a variable. And now if we check the coordinate reference system for our points, we will see NA, it has no coordinate reference system. So what we would think is, why not go ahead and do this? Write our CRS Bonn into CRS points. But if we try to do this, we get an error, unable to find an inherited method for function CRS for signature data frame. So our variable points is a data frame, looks like this. And if we try to assign a CRS, it doesn't know what to do with it, because a data frame is not supposed to have a spatial reference. A data frame doesn't have any spatial reference. But you know what does have a spatial reference? A so-called spatial points data frame. So it's very converse to our spatial polygons data frame, which is where Bonn is saved. We can also create a spatial points data frame, which is basically just a data frame with spatial reference for points. And the command to do this is called spatial points data frame. It creates objects of class spatial points or spatial points data frame. And that is what we want to do. We want to convert our data frame into a spatial points data frame. So what we do is we create a new variable called points Bonn, and we create into this variable, we create a spatial points data frame, and the data it's based on is points, and then I think the rows, the first one is row, the second one is column, so column 1 and 2. So we only base it on the X and Y coordinate, and we don't take the ID, because X and Y is our spatial reference here. And then this is the data. I think if we run this, something will happen. Yes. So now we have converted this data into a spatial points data frame. And if we run this, we can have a look at it. Again, you see 8 features, which are all 8 points. We see the extent. We see the variables, which is X, Y, and ID. And then we see here, coordinate reference system is still an A, right? So that's an issue, because we wanted to have a coordinate reference system. But now, since we now have a spatial points data frame and not just a normal data frame, we can just assign it our coordinate reference system. So here again, coordinate reference system for points Bonn shows it has no coordinate reference system. And the way this works is you can just define any coordinate reference system and write it into the coordinate reference system of an object. And the syntax here, you can just look up. You can just look up coordinate reference system. I don't know, if you want to use WGS 48 UTM zone 32, then you just Google this and then R code behind that, and then you can copy it in here. So this coordinate system is WGS 48, which is a datum, and then UTM zone 32 north, which is where Germany is in. And if we now assign this First of all, let's do this again and call our coordinate system just to find out if it worked. And now if we call our coordinate system of this layer, of this variable, sorry, I keep talking about layers when we started with spatial data, but it's still a variable technically. We see the coordinate system we just assigned. So if we plot this now, we will see it looks a bit different, and it's now actual coordinates. Let's give it both axes. Axis. Whoops. By the way, I do this with little empty spaces between arguments and functions to improve clarity, but you're allowed to do this, right? It doesn't matter. It doesn't change anything. But please use it consistently. So don't do it like this or like this, and then in the next function you use it like this. So choose one style and go with it. Okay, so these are our points. They now have a spatial reference. But one issue we have, and we see this if we look at the y-axis and the x-axis, these values, these coordinates look very different from the coordinates we had when we looked at the Bonn layer. You remember? These are very different coordinates because this layer has a different coordinate system than the other layer. What we want to do now is we want to transform our coordinate system in the points Bonn layer to the coordinate system of Bonn, so we can plot them together, right? We want our coordinates on here because, spoiler alert, these points are in Bonn. Okay, we had one question in the chat regarding earlier. The indexing up here, I think. Yes, when we created the spatial points data frame, we used an index here. And the second part of the index is the sequence 1 and 2. Doesn't really matter if you do it like this or if you put a comma here, but I would put a double dot here to make it more clear. And this is a throwback to our, I think, very first or second lecture, I'm not entirely sure, but this way we index the first and the second column. So the second position behind the comma here is the columns, and the first position before is the rows. So if we wanted to select the first two rows, we would do it like this, but we want to select the first two columns in this context of this function.
Yes, and more specific, or I think the question was probably why there is the comma. So we select all rows. That's the thing, you know, the comma, the
Yes.
space is empty, but that means we select all rows but just columns 1, 2, 2.
Yes, sorry. Yeah, you're exactly. You're correct. If we just want to select one row, for example, we can put it here, and then it selects the first row and the first, like the entries in the first row and first and second column. Or if we put it like this, it selects the first two rows, but only the first and second columns. It's index syntax.
Was it clear? All right.
Okay.
Yes.
All right. Let's go back to transforming our coordinate system. That's very easy too. There's a function called sp_transform. There's a function called sp_transform. There's actually multiple of these functions. I just want, or multiple entries in the documentary, but I want this sp_transform for map projection and datum transformation. So it's a function that you can use to transform, to reproject your data. It's like going in QGIS or going ahead in QGIS or ArcGIS, right-clicking the layer, adding or changing the coordinate system, just as a function. So what we want to do is we want to take our variable called points Bonn and use this function sp_transform on our points-Bonn layer. And we, as a coordinate system, we could clarify by copying not this one because it's the one from points-Bonn, but the one from Bonn over to here. But or we just call the coordinate system from Bonn. And if we do like this and run it, and then we plot these on each other, you will see the coordinates are correctly inside of the shapefile, just as we would expect. And here you have the here you have X and Y axis, just so you know the coordinates are the same. So this is super simple. This part here is just to make our life easier, right? Because we don't have to use it like this. We could also, because this is just a CRS argument, we could also just copy this and give it as a string like this. Oops. But it's much less convenient. And it's longer and looks worse, in my opinion. So we don't do it. We just use the CRS function to call the CRS from Bonn and transform with that. So that's how you transform a coordinate system. It's very important to keep in mind because you need it if you work with geolocations. The final thing we do is we export our newly created points layer. Because if you remember the points layer, originally it was just a table with coordinates. And now we have it as a spatial data set, so we can export it as a shapefile. And the function to use is conversely to read OGR, write OGR. And you just use write OGR. You give in the layer you want, the variable you want to export. In our case, that's points-Bonn. And then you give it a name. Why is it like this 2 times? I'm not entirely sure. Let me check before I delete anything and or like say anything stupid. Okay, so one is the data source name and one is the layer name. So this one is how the layer will be called in our folder. And I'm not really sure what the data source name does, but sometimes I think it does need it. And then you have here the driver, and the driver is basically the file type. In our case, we use S3 shapefile because we want the shapefile, but you could also use GeoJSON, for example, or whatever format you want. It doesn't really matter, it's just which format you want. And then if we use this, you will see that in our corresponding folder, there will be a new folder. And inside of this folder is a shapefile called points-Bonn. And this is our spatial data set we created in R. And that's also, I just remembered what this does. If you give this argument, it will create it into a folder. And if you don't give it, and this is the folder name basically. So maybe we do it like this. This is the folder name it will be created into, and this is the layer name. Yeah. But this is really, it should be really easy. It's your final step in this lecture task. And now I think you deserve the break.